a last example of being able to find the areas of polar functions, we're going to try to find the area that's outside of the function f at theta equals 1 plus cos theta, and then inside the function g at theta equals 3 cos of theta. First thing we should probably do is graph this. So we're going to use a graphing utility, and we're going to just say that we have 1 plus cos of theta, right? And that's going to give us a cardioid. Okay, so it's going to be outside of this cardioid, but inside 3 cos of theta, right? And so essentially what we're doing is we're just looking for this crescent moon sort of like structure right here, or shape, okay? And we're going to try to omit this right here. So if we could figure out what these points of intersection are, then we'll be good. Okay, so graphing this. Okay, so we have a dimple here, and then we have a dimple here, and then we have like a remaining, it looks like this, and then we have a circle, and I know this isn't good, sorry, all right, but we're really looking for this area, okay? And so if we can find this point and this point of intersection, that'll help us to be able to figure out what the bounds are going to be for this, okay? So let's set these functions equal to one another. So we have 1 plus cos of theta is equal to 3 cos of theta. Right? We're going to subtract cos theta. So we get 1 is equal to 2 cos of theta, or 1/2 equals cos of theta. And we know that this is true at the angles 5 pi thirds and pi thirds, okay, for theta. Okay. What might be easier for us is to remember that 5 pi thirds can be written as negative pi thirds. Okay. And so if we think of this as the initial point, like A is negative pi thirds and B is equal to pi thirds, that's going to be our angles. All right. So think about it this way, that if we're going from the pole, okay, this is our theta of negative pi thirds. And then this is going to be our pi thirds. But of course, right in the middle is 0. And so what we could really do is just look at half of the area and then double it. Okay, so if I were to take a cross section of this just inside quadrant 1, it would be something like this, all right, where it intersects, okay, somewhere. And I know that isn't good, all right, but what we're really looking for is we're looking at right here is a point of intersection, all right? And we would get something like that. And then we would just double it, where right here is going to be pi thirds, and down here, so this is going to be the angle for theta, and then we have 0 right here for theta. All right, so the way that I'm going to set this up is I'm going to say 2 times 1/2 of the integral from 0 to pi thirds. And then I'm going to take the outer function because we want it inside of the 3 cos theta. We're going to say 3 cos theta squared. And then we're going to subtract out 1 plus cos theta squared, d theta. Now we can FOIL that out. And we're going to get 0 to pi thirds of 8 cos square theta minus the quantity of 1 minus 2 cos theta plus, or excuse me, 1 plus cos 2 cos of theta plus cos square of theta. Or the d theta. Right? And then we have an 8, and then we have a cos that's negative there. And so that's just, oh, this should be 9, excuse me. Not sure how I got 8 out of that, but that should be 9. And we square that 3 there. So sorry about that. I was probably thinking ahead. And when we combine this 9 cos with this negative cos, we're going to get 0 to pi thirds of 8 cos square theta minus 1 minus 2 cos theta, d theta. All right. Now, we're going to have to use the power reducing formula on that 8 cos square of theta. All right. So our power reducing formula for cosine Remember, cos square of theta is equal to 1/2 plus 1/2 cos of 2 theta. Right? And so we're just going to substitute that back in, and we get 0 to pi thirds of 8 times 1/2 plus 1/2 cos of 2 theta. We still have the -1. We still have the -2 cos of theta. And then we have a d theta. All right, I probably don't need this second bracket in here. And then finally, we're going to combine some like terms. All right, and the only ones we can combine, 8 times 1/2 is 4, and then we have -1. So I think the simplest integral we can get before integration, 0 to pi thirds, 3 from the 4 and the -1, plus 4 cos of 2 theta minus 2 cos of theta, d theta. All right, now we can finally integrate. And the integration is actually really basic for this one. The only thing that we have to remember is that we have a 2 inside that interior angle. So we're going to have to divide by 2. So we're going to get 3 theta plus 2 sine of theta minus 2 sine, or this should be 2 sine of 2 theta, excuse me, and then minus 2 sine of theta from 0 to pi thirds. All right, now we just substitute pi thirds back in. And so we're going to get 3 times pi thirds plus 2 sine of 2 times pi thirds minus 2 sine of pi thirds. And then we substitute 0 back in. So we get 3 times 0 plus 2 sine of 2 times 0 minus 2 sine of 0. All right, so some good news. Actually, lots of good news. So 3 times 0 is 0. 2 sine of 0 is 0. And then 2 sine of 0 is 0. So the whole second expression is just going to cancel out. 3 times pi thirds is going to be a pi. We have 2 sine of 2 pi thirds. All right, so sine of 2 pi thirds is going to be √3 over 2. Okay, so we just use our unit circle to be able to evaluate that. And then we have a -2, and sine of pi thirds is going to be another √3 over 2. And so notice that these are opposites, they cancel out, and we're just left with pi. Okay, and pi is going to be this region, both of them. Okay, because remember, we doubled the region. Great. So hopefully that helped you to understand how to find these areas that are involved with polar coordinates. Okay, areas in polar coordinates are a pretty tricky animal because of the graphing and the limits, and then also the techniques of integration required to find those values. All right, so one more section, and we're just going to take a look at the arc lengths of various polar functions.